In this lecture series, we're going to talk about color and tonal value. So let's start with color. So color is just an illusion created by the brain to make sense of the physical world. Objects in the real world don't have any color, but what they do is absorb and reflect light that comes out of the sun, and so the rays bounce off the object. Some of them get absorbed, some of them reflect, and those reflected rays come into our eyes, hit our retina, and our brain then interprets that into information and forms an illusion in our heads that make the world appear colorful. It's actually no color at all. So color is therefore a function of light, and it has great significance to us, as you would imagine now, knowing that it is something our brains essentially invented to deal with the world. And so you can see little images here that, the light rays are coming in, and when they hit an object, whatever gets reflected off of it will appear that color to us. So technically, light that's bouncing off, that's blue, is why we see a blue object. Now, other animals and other species don't see color the same way we do. And we'll get more into that in a minute. I'll show you some really cool images. I know this is kind of mind-boggling when you first find out. I remember the first time I learned that color was not real. It was just totally imaginary in our heads. It was just mind-boggling because we assume that because we see it, it's real. And it just isn't. So, and this just kind of just goes to show, right? So if we're dealing with red, green, and blue, which are light colors, then what we see is contingent upon what gets absorbed and what gets reflected. And the same thing with CMYK, which are the print colors. So red, green, blue, cyan, magenta, yellow. And we'll talk a little bit more about those. Because we need light to make color, the less light there is, the less you can see color. Colors also appear differently during the day. That should say day and night. And that has to do with the fact that light itself has a color to it. In the morning, the light is cooler, and as it moves towards noon, it becomes white, like neutral. And then as it moves off towards sunset, it becomes reddish. And that has to do with the fact that our sun is spinning, and blue and red have to do with how the direction it's moving. And so for any of you that have learned anything about astronomy, you'll know that the red-blue color shift indicates which way a star is spinning. And it's really, really cool. But that the red and the blue, therefore, then affect or tint what we see because they're adding that on top of it. So the visible spectrum, and what that means is visible to the human eye, was defined by Isaac Newton by reflecting light through a prism. And you can see an example there of the light coming into the prism and then it breaking apart into the rainbow. And then you see that tiny little sliver on the very bottom of all light, of all wavelengths. And there are animals that can see to the left and to the right of that. They can see colors that we can't. It's just really fascinating to learn about this because we can do photography, and I'll show you in a couple slides. We can do photography that shows what they see. And so here you see essentially there are, radio waves, microwaves, infrared, then human visible light, ultraviolet, X-rays, and gamma rays. So that's it. That's all we can see is that narrow band of the visible light. And we just keep zooming in and further in. And then you can see it again here. So you can see what we can see. So to the right of red is infrared. We can't see that. It starts to fade off, and then we just can't see it. And then to the left of the other side is ultraviolet light. And so what we're going to do is take that visible spectrum in a minute and bend it around on itself to create the color wheel. And this is where the color wheel comes from. Okay, so here is a flower that is photographed to see the way our eyes see, and then the one on the right is what an insect sees. And we did that by using an infrared camera so that it captures light. So you can see that all these things, all these colors are a construct of the brain, depending on how the brain processes those light waves that bounce off of it. And so it was Sir Isaac Newton. And you're noticing I'm talking about a lot of mathematicians here and physicists, because color actually is based in physics. Um, and a lot of what we do so far, we've learned about the principles and elements of design being based on psychology. And a lot of what we do is actually science based. And often artists just have this natural ability that know how to harmonize or balance things. Um, but it doesn't mean that you're either born with it or you're not. You can learn the rules, and that's why we're covering them. For one, is so that you know what they are, but also that you can understand why they're the rules. It's not like somebody just made them up one day. They're based on math and science. And so Sir Isaac Newton started the color circle after he noticed that the colors in the visible spectrum actually were similar, right? Because red and blue make purple. And so he spun it around and it became the precedent for what we refer to as the color wheel, which is the basis for modern color theory. And so this is a 12-point color wheel. I'm sure you guys have seen all kinds. There are different gradients. There's different ways of looking at these. Some of them go from white in the middle or black in the middle to white or black on the end so that you could see the full range. And again, we got another physicist who created the 12-point color wheel. And we use this when we talk about mixing colors, and also when we start talking about color harmonies. And what a color harmony is when the colors that you select work so well together that it creates what is known as a balanced color scheme. And we're going to get into how to do that. Okay. The 10-point color wheel came next, and you can start to see it starts to fade a little bit towards the middle. That the pure hues are on the outer end, and then it fades as it gets toward the middle. So color can be additive, which is light, or subtractive, which is pigment. And if you've ever seen two people argue over primary colors, it's hilarious. I mean, it's because there is no one answer. They're both right most of the time. They're looking at different things. So the people that talk about red, green, and blue, or red, blue, and yellow, and then therefore they say that black is a color, they are correct. When it comes to additive colors, you start with that blank white page and you begin to add color on top of it. And then once you've added all those colors together, it gets black. It becomes black. So in that instance, when we're talking about on the page, white is not a color and everything else is, including black. Then on the opposite hand, when you get to the subtractive primary colors, now we're talking about light. So the lack of light is the lack of color, therefore black is no color. And when you add them all up, you eventually will get white. It's that light that went into the prism in the first place. And so in this case, when you're talking about pigment, you're talking about additive. White is not a color. White is the absence of color. Black is a color. When you're talking about light, black is not a color. It's the absence of light, therefore the absence of color, the absence of colored light, if you will. And white is a color. So you'll watch people fight over this. I've watched people like insult each other over this. It's hilarious. When they're both right. Actually, I've argued with people over this too, but well, I argued from the perspective that it's both, that both are right. And, people's, they know what they know. Okay, and so here you go. Here's another example showing you that pigments versus light, just a different way of looking at them. Okay, and then just the basic colors for working with light are primary colors, which are blue, green, and red. And I know primary colors are blue, yellow, and red when you're talking about crayons. But when you're talking about light, you're talking about blue, green, and red, and cyan, yellow, magenta. So primary colors are the ones that cannot be derived from mixing any other colors, and that is because their wavelengths are what hit the object and bounce off. They're broken down as small as they can. Secondary colors are a combination of those different wavelengths. And then when you see CMYK, it stands for cyan, magenta, yellow, and black. And the B was already blue in the other scheme. And this is how layering ink and color works when you get into printing. Colors can be warm or cool, and therefore have the power to suggest a mood or emotion. And you can see cool color scheme on the left versus warm on the right. And just looking at those, you see how they make you feel different, or you feel differently by looking at them. And that has to do with the fact that color has a scientific significance to us. So there are 3 key properties of color: hue, value, and intensity. Oh, I got those backwards on the page, didn't I? Hue, intensity, and value. However you want to put them together. Hue is the primary color itself. It's the base color. Intensity or saturation is how potent it is. And then value has to do with the darkness or the lightness. And then in each of the boxes below, there's a pink hue, a blue hue, a yellow orange hue, and a lime green hue. And then within that, we've broken these colors down further by intensity and by value. And that's why ultimately we as humans can end up seeing a million different colors. Because once you put together the color, the visible light that we can see, along with intensity and value, you've got a million different combinations. So hue is color in its purest form, and it is, like we were talking about earlier, it's usually either the outermost band on the color wheel or it's the middle, because some will go from this and they'll start to add black and fade to black. And then we see this broken down to segments. Here it's yellow, and then it spins around into segments so that they have easily identifiable names. But what really it is, it really looks like the one on the right. They blend together, and you end up with all those different colors. These colors have names and numbers. Every single color has a name and a number. And Pantone uses them, Photoshop uses them, and they're all unique and identical and individual. And it helps you it helps you identify or pick an exact color so that when you go to print something, you won't necessarily get what's on your screen. You'll get what that color is once it's been printed out with ink. And that helps make sure that you're getting true colors. So value refers to the lightness or the darkness of a color. Red is the hue. Pink is the tint, meaning we added white to it. Maroon is the tone, meaning we added gray to it. And burgundy is the shade, meaning we added black to it. Okay? And so there are 40 different tints the human eye can see, or 40 different tints and shades of any one hue. And so then tones are like in the middle. So he's got all these different combinations that add up. And then finally we get intensity, which is the brightness of the color. So it's referred to as saturation or chroma. And intense colors demand attention. I'm going to stop this video here, and we will continue in the next.